I want to be like closer to you. So this is more like, okay. So wonderful talk, Christina. It was amazing. It was like also overwhelming. Now you see like all we can do with complex systems. So this was really an amazing introduction. I will start telling you a little bit about me, and then what is going to be my course. And then I prepare for you guys like a class. So this is going to be, I hope. So I don't really know what your background is. So we know we have different backgrounds. We are going to know more about you this afternoon. But please feel free to interrupt me. Also, you can interrupt me in Spanish or in Português. Eu falo pouco de português. Eu compreendo mais do que falo, mas você pode falar. So the language is not a problem, right? And if I don't understand your Portuguese, a friend of yours is going to just tell me what you said. So this is for you guys, right? So it's a school. So this is all you. So, and I don't really, I'm interested in finishing all these slides. So I prefer actually not. Okay, so I'm Ana Amador. I'm a professor at the physics department in the University of Buenos Aires in Argentina, and a researcher at the CONICET, that it's a research council, but we do all the things in the same place. So we have two institutions, but we only work in one place. Okay, so I do interdisciplinary work in neuroscience. So I started in physics at the University of Buenos Aires, and I did my PhD in physics. So in the University of Buenos Aires, we still don't have interdisciplinary PhD programs. So you do what you do, and then you can put interdisciplinary things inside. And I did my PhD kind of long ago, so I finished in 2009. And we were starting with interdisciplinary. So during my PhD, I also did experiments, not only modeling, but experiments. Okay, I will fall from here. And then I went to do a postdoc at the University of Chicago at the Organismal Biology and Anatomy department. I put this because this was a neuroscience postdoc. My boss was a neuroscientist, and I went there to learn how to do experiments with brains, okay? So I wanted just to be there. So I went there to learn the techniques, but I ended up learning much more. And I will tell you about this in the last lecture, and I hope you can take it like take home message that it's not just the techniques, it's the way you approach the problems that is very different from biology and from physics. And we can when we can work together, we really do science. Okay. So, so I work in the Laboratorio de Sistemas Dinámicos. And our goal is to shed light in the dynamical mechanics involved in the perception and generation of complex sounds, and to study the brain in the peripheral system in this process. So we work with birds, and I will tell you about it in the last lecture, or maybe the next one too. But I just wanted to tell you that we, in our lab, we do behavior and recordings and analysis of that behavior. We also do recordings of muscle and respiratory activity. We do neural recordings, but we integrate all this with dynamical system models. So this is a really interdisciplinary lab. And in our lab, we are physicists and biologists working there. So Fiamma is my student, and she's from biology, but she's working in the physics department because that is our lab. We are like really highly interdisciplinary. Okay, so let's go to the talks, to the lectures. So the first one is going to be Introduction to Nonlinear Dynamics and Excitable Systems. I will also hope to talk about a little bit of dynamical models for single neurons. if we get there. If not, it's going to be just in lecture 2. But I wanted to share with you some experimental data. I thought it's going to be interesting for you guys to see, well, this is how you record it, how you can do it in Latin America, right, with not so much money in your pockets. But what would you do with data, and how do you process, and how can you get information from there? Just the first hand of that. And the last one is the neuroethology perspective. So I will tell you what neuroethology is, and I will tell you a little bit more about my work, but also emphasizing the nonlinear models and how we can use nonlinear models to understand more about nature. And all of this can change, okay? So not the problem with that. Okay. So this lecture, I want you to participate. So I know many of you know these things. I think it's fine. I think one's feel comfortable when you hear things you already know and you say, yes, so this I know it, I'm fine. So it's a good way of starting a school. But I just wanted, and if you say, and you can also say, we are getting really bored, just go ahead. I can, you can interrupt me. But I just wanted to make sure that we are in the same page with all these concepts. And especially because if you know the stuff, it's okay. But people that maybe it's not so familiarized with the concepts, I think it's a good way to start. Okay, so we are this school is going to be about dynamical systems. Christina told you about it, but I want you to tell me what is a dynamical systems. What would you define, what would you say a dynamical systems are? I want you to participate, I told you that already. Yes.
Can be discrete like a map or continuous like differential equations. And the mathematicians say that we also need a measure, but I don't know how this exactly works.
Yeah, great.
So space and time evolution operator.
Great, amazing, exactly that. So what you say, so, okay, I will try the names. So tell me your name. Gabriel, that I will remember. My husband is Gabriel. Okay, so great. So what Gabriel is saying is that we have a set of variables. That is what he said. Well, we have the state, something that defines the state, what the variables that will describe the state of the system, and then a law that describes the evolution of the state variables with time. And so exactly that. So this is the important things of dynamical systems. So this evolution of the state is how the state system is going to behave in the next moment, depending on what was the previous moment of time, okay? And so let's go an example. So I just started with the Hodgkin-Huxley modeling because I think everyone has seen this. So who has seen this model before? Studied this? Okay, nice. I thought everyone was going to. So I'm really happy because there are people that never have seen. Well, great, amazing. So let's start. So this is a dynamical system. Why? Because we have 4-dimensional dynamical systems. So we have 4 variables and the evolution of time. So this is the derivative against time. So these 4 states are, so it's the voltage, and then this N, M, and H are corresponding to the gating variables that relate to the potassium and sodium channels in the system. So this is the first model for a neuron, right? So at least I think everyone knows that. And the evolution law is given for this 4-dimensional system ordinary. So these are differential equations. So you have many other different equations to describe the evolution of time, but this is what it is. So this represents the ion currents. So the question is this dynamic? So this is a dynamical system, 4-dimension, etc. But the question is this nonlinear? So how can we say if this system is nonlinear? So we have the variables, and then we have functions and parameters. Why we can say that? So the question is this nonlinear? Yes and no, and why? Nonlinear. It's a very long equations, right? So it's long equations, and we are talking about nonlinear, but why it's nonlinear? Exactly, yes. So we have this, right? So nonlinear, we are looking for nonlinearities, functions that are nonlinear, so these exponents are saying, well, this is at least nonlinear. We don't care how these functions are, so these are functions relate to the voltage, but independently of how these functions are, this is already nonlinear because the variable are related here as a nonlinear function, okay? But moreover, this is very nonlinear, not only because it's long, but because all these functions are highly nonlinear, okay? Bien. So we are going to go back to these equations later, but so the nonlinear dynamics are going to study these systems. We have nonlinear rules like this one or these ones that will interfere with our dynamical systems, and the dynamics part is that the mechanisms responsible for governing the temporal evolution of the system. And as Christina mentioned, the thing with the nonlinear dynamics is that we cannot separate these equations in more simple parts. So that is the thing that we can do with linear dynamics. If we have a linear system, we can just put different parts, and then we can integrate, summate those, and we will have the whole picture. We cannot do this with nonlinear dynamics, but so we have to develop some other rules. And I will tell you a little bit more about this. So going back to Gabriel's definition, I only told you about differential equations, and we were telling a little bit about this. But also we have maps. And this is what Christina mentioned. So the logistic map is a very famous map because it's very simple. Actually, it looks like much more naive than these guys, right? But this even very simple, but nonlinear. Why is this nonlinear? Because you have x and x here. So when you do the distributed thing, so you have a linear part, but then you have x squared. And just this kind of, I don't know, naive stuff can give you chaos, as Christina was telling you about. So depending on what you look, this system could be much more complex in the evolution of time than this. But defining what is complex or what is more complex, if one thing is more complex than the other, that is a hard thing. So I won't tell you about maps. We will focus on differential equations. And I wanted to discuss with you a little bit about phase portraits. And so the power of dynamical systems approach to neuroscience and also to many other science, because these, as you will see, are very general approaches, very general tools that we can use for, so today I will focus on neuroscience and I will be focusing on neuroscience, but as you saw from Christina's talk, you can apply it to almost anything. Anything that it's moving, okay, that it has an evolution of time, you can apply it there. Okay, so let's see the power of these kind of approaches, but focusing in an example of neurons that I think, like this is in school in neuroscience, I think maybe all of you are kind of familiar with this. So this is representing the membrane potential, and this is an scheme say, well, this is how the membrane potential evolves with time. And if you put a stimulus here, you get what you have a postsynaptic potential that it's a little blip. So this is the resting state. And if you have a stimulus, it goes up, but then it goes back to the resting state. So how you represent this with phase portraits? Well, in the first portraits, you put the variables of with what you are describing your system. So for example, membrane rotation and for example, the activation gate N. And this is a representation of what you are seeing here. So what this is showing you is that, for example, if you start here, so this is a given value of the membrane potential and a given value of the activation gate N, this will evolve to this point, that is the equilibrium point, okay? So here I'm just drawing the value of the potential, but I can also draw another line and put where the N equilibrium is. So it doesn't matter where you put, where this starts, what the stimulus is, it will always go to the equilibrium. And this is the representation in the, this is the first portrait of what is happening. And this is a stable equilibrium because it always goes there and stays there, okay? That is what is showing you here. If you don't put another stimulus, it will just remain there. Okay, and so I wanted to highlight that it's amazing all that we can say about this without knowing the equations. We just know how the neuron is behavior, and we can already say things about the dynamics. And we don't know the equations, and we don't know even how many number of variables we need for describing this neuron, okay? But for describing what is happening, this is enough. So the spikes, here they are. So this is a representation of, well, this is what we were seeing just before. But if you put another stimulus, so a bigger stimulus, you have spikes. And how you represent the spike in a phase portrait, again, this is membrane potential and N. So this would be, if you start from a different initial position, then you will have a long exploration in the phase space to get finally to the equilibrium. This goes, returns to the equilibrium, but with different evolutions depending on the initial states, okay? So this is what I just say. So small perturbation, small excursions, and larger perturbation is a spikes response. So this is what we call an excitable system. So this is a neuron. Just to mention, in the brain, for example, you have other cells that are not excitable, that are called glia. And actually, those are very important. We don't know enough from them. They are not spectacular spikes, but those are not excitable systems. They don't behave, they don't do spikes, but this is just to say, well, it's not that all the information is in spikes, but for my class, I am just going to focus in the spike, in the information carried by the spikes, but it's not all the information, right? Okay, so this is an excitable system. And another possibility that you have is the periodic spiking. So it's not that you go back to the equilibrium position, but you have in the phase space what you call a periodic orbit. that is saying, well, this is going, so for example, if you start here, then after a period, you will go to the same place and the same place and the same place. So this is a periodic movement evolving in time of the membrane potential. And in the phase space, you will see it at, say, limit cycle or a periodic orbit. So we are going just to work with these 3 states, and we are going to discuss a little bit about this. Before moving forward, I wanted to say that equilibrium and limit cycles can coexist. So a neuron can be switched from these equilibrium states to periodic states, but by changing parameters in the system. So how would you see going from here? How would you see a neuron doing the transition between an equilibrium and a periodic state? This looks like this. Here is the resting mode, but then if you're changing some parameters, this can enter in a spiking mode, and then go back to the resting mode and then spiking mode. So this behavior, this dynamical system behavior, can be achieved from very different mechanisms. So this can be driven by parameters, or this can also be what we call like auto-oscillations. So pacemakers can do things similar to this. So this is very vast, but this is just an example that you can alternate between these 2 dynamical evolutions, and this is how you will see it in the neural data. So Christina mentioned a little bit about bifurcations, but I wanted to make sure that everyone knows what a bifurcation is and how we see it in the data. Okay, that's why. Okay, so I spoiled it. I wanted you to answer this, but bifurcation is related to qualitative changes in the system. So let's see if we understand this. So is this a qualitative change? So this is one state, the resting state, no spikes here. And this is an excitable state, so we can get spikes. So if the system goes from A to B, is it going through a bifurcation? Who say, yes, it's going through a bifurcation? Don't be afraid, you won't lose. Okay, who say it's not going through a bifurcation? Not going through a bifurcation. So if this goes from here to here, it's changing some other thing, but not a bifurcation. Don't be afraid, guys. Okay, so the ones that say no, why? Why this is not a bifurcation? It's a quantitative change. Okay, so tell me your name. Bruna, it's saying it's a quantitative change, not a qualitative change. And what do you mean by that?
The behavior is the same. There's a spike, there's an excitability curve, but the amount of amplitude of the signal is different.
Okay, yeah, we're going there. So it's a quantitative thing. And we can also interpret it like this. If we look at the phase portrait, it's more simple than looking at this. That's saying, well, in this state, in A, we have this equilibrium, but here we have the equilibrium. So actually, A is included in B. And this is what Bruna is saying about quantitative changes. That quantitative, it depends on what stimulus you are using. So in the first portrait, what are your initial conditions? And then, as in the dynamics, this is including, depending on the initial condition, you can have A that is the same as this one, or you can have a spike, okay? So you see different things, but this is not a qualitative change. Okay, This is not a qualitative change, so no bifurcation, okay? So this is why phase portraits are really much more clear than this, because here you are drawing all the dynamics available, and here it's very more straightforward than this dynamics is included in all this thing, okay? Okay, so the other example was, well, but what happens, so now if you go from B to C, do we have a qualitative change here? Because here they are all spikes, right? Spikes here, but what is the qualitative change? So I see some things say, yeah, we are more confident. Why? Why a qualitative change? It's periodic. We have a limit cycle. Jordi, I'm sorry. I'm giving you so much trouble. I will just yeah, okay. But, I mean,
Don't worry.
this poor guy was in Madrid yesterday evening, okay? So he's amazing. Okay, exactly. So this, we have a periodic orbit, and here we don't have a periodic orbit. We just have this limit, this stable fixed point. We will see that we probably have something else, but not a limit cycle, not a periodic orbit. So yeah, so we can say, so and again, here is very clear that although the trajectory may look alike, because we are all spikes, the difference is that one will just stop here, and the other one will just mount in this periodic orbit. Yes? Okay, I didn't hear you. Okay.
Sorry. What if we had the stimuli A before the spikes in the second example? Then would have a qualitative change just because it's periodic?
You say the stimuli A here?
Yes.
Yeah, so you will have the so that you will have also the qualitative change. The only difference is that this will just be, you will have the stimulus, maybe you will see some variation in the spike depending on where the stimulus is, because if the spike has already started, no other stimulus you cannot interfere with it. It's all like internal dynamics. So you can see also blips here before, but this would be before going, so this would be, for example, you do something here, and you will see a blip here, but once it has entered the period, so for example, you start here, you make this A stimulus, and you will see that, but then this will evolve to this limit cycle, and then it will just stay there, okay? And then it wouldn't matter. Okay, any other questions? Okay, I will just stand here for a little bit. Okay, yes, we have a bifurcation, okay? Okay, and so how do you see that in data? So in data, the way of going through a bifurcation is that, for example, ramping up the current you are injecting to the neuron. And this is something you can do experimentally. You just poke the neuron and then put some ions there, and so you kind of can do a ramp of current that you can measure. And before, for example, you are in a stable equilibrium, and when this value of the current starts going up, then you have a transition, and then you start the oscillations. And also, maybe if you keep on increasing the current, you can change this limit cycle. If you are moving the parameters, sometimes, for example, you see that it is fast firing slower than here, for example. And then you can just be like changing the shape of the limit cycle, so you will see changes in the spikes. But this is how you see a bifurcation in the data. Okay, so let's look at what bifurcations you can expect in neurons, changing from a resting point to a periodic spiking. Okay, so the figures that I was showing you before, you have a resting state and a limit cycle. And you can go from that state to other, so you will have a bifurcation, a qualitative change, but you can go from that state to another in a different ways, with different bifurcations. And I just wanted to discuss a little bit about this topic. So, for example, you can have this kind of dynamics. So, again, so I will talk a little bit about this. If you are really lost and you have never seen anything about the dynamical system, we can discuss a little bit more in the hands-on course. But let's see. So what it's saying here? So here we have a node, a saddle, and this spike and limit cycle. So this is a limit cycle. And this is a repulsor fixed point. So this system, what it's saying is that depending on the initial conditions, the neuron may just decay to the node or will burst. So for example, so this is the phase space, and if you start initial conditions here, you will be attracted to here. Or if you start here, you will probably be attracted to this stable point. But if your initial conditions are here, you will be repulsed and you will just get oscillating. Okay, so, but the bifurcation is when the saddle and the node collapse. So this is the bifurcation point. You have el saddle and the node, and they collapse and they disappear. So this is going through the bifurcations. So this is a qualitative change because you go from a node and a saddle that collapse, and then you have nothing there. They collapse and disappear, okay? And so you just, the bifurcation is because you just get to the limit cycle, okay? In the next class, Jesus will tell you more about this bifurcation, but as I wanted to show you how you will see this in neurons and how you can get different behaviors in neurons with this bifurcation. Okay, so although maybe you won't see enough the bifurcation if you stay in the initial conditions here, you will just say, well, limit cycle, limit cycle, limit cycle. I don't see any qualitative change. That is why when you are exploring your dynamical system, you have to be very careful how you explore the initial conditions. Because if you put in your simulation initial conditions from here, you won't see any change in the dynamics. So this is why you have to be very careful, because the change here is when you put initial conditions around here that you will see this saddle node, and then you won't see it anymore, okay? Okay, are we okay with this? Okay? Not too bored? Okay? We are okay. Okay, another bifurcation having this saddle node is when it's not that you have a limit cycle, but what we call an invariant cycle. So again, the saddle and the node collapse in the bifurcation point, and then you just have this circle. Let me just tell you a little bit how you look this saddle node on an invariant circle bifurcation, because it's not so obvious at this. So this is another representation, but this is an actual simulation. So here you have the node, the saddle, and the repulsor, that what is here, now the saddle, the node, and the repulsor. And this is how you see the trajectories. So if you put an initial condition here, you will just go all the way and just go in the resting point. And this is how you will see it if you, so this is a phase portrait x and the velocity, but if you represent x and time, this is how you see. The spike is just going from here to all the way here. And the PSPs that we were seeing before saying, well, you will just start near the equilibrium, you just go to the equilibrium, okay? When this is the threshold where the bifurcation occurs, and so this saddle and this node collapse, and you just get to this circle, and this is why you have spikes that are occurring continuously on time. But what I wanted, and then if you move away from the bifurcation point, you continue to have this circle, but this changes in shape. So the U doesn't change qualitative things because here you just have this limit cycle. But you see differences in the evolution of X versus time, and X can be voltage in your cell, in your neuron, or it can be any other thing that it's oscillating. Okay, this is just an oscillating with time. And what is interesting here is that we have what we call a saddle node ghost. That what it's saying is that near the bifurcation, you can still see the shape of the spike. So this is the spike or the ghost of the excitable system. This was the excitable system. Excitable because depending on the initial conditions, you can make like a huge exploration in the first portrait until going to the equilibrium, or small going to the equilibrium. But here, you're oscillating, but you still see this excitable system. And you have to be very far away from the bifurcation to have a more like regular oscillations. Both are limit cycles. But this is interesting to have in mind, because depending on what you want to simulate with your model, this could be really interesting, how you start oscillations, okay? Any questions? Okay, we're fine. Let me see, so how much time do I have? So 20 minutes? Okay, great, okay, nice. Nice. So another bifurcation. So this is different. In this configuration, we have an stable fixed point, an unstable limit cycle, and a attractor limit cycle. Okay? So here, depending on the initial conditions, it can change a lot. So if you start here, you will oscillate. If you start here, you will also oscillate. Maybe you get a little round until you get there, depending on the parameters. But if you start here, you will just get to the resting point, okay? So again, we have two possible states, resting point or limit cycle. So in the bifurcation, what happens is that this stable limit cycle gets like shrinking into the fixed point, and they shrink until they collapse. What it collapses here in the bifurcations always suffer some collapses, and here what it collapses is the fixed point and the unstable limit cycle. They collapse, so when they collapse, these fixed points change stability, and now you have a repulsor. So in the bifurcation, you only get to this limit cycle, and you don't have this B-stable state anymore, okay? So again, you pass from two B-stable points to only bifurcation. Here, it doesn't matter where you start, you will always finish in the limit cycle, okay? So these are different things of going through. The last one, so you have just an equilibrium, and then this equilibrium loses stability and gets repulsor and a limit cycle. So this is the Hopf bifurcation. Probably you all heard it. So this is why these bifurcations are called Andronov-Hopf. One is subcritical and the other one is supercritical, because that depends on how is the stability of the limit cycle before and after the bifurcation. But this is another different way of starting oscillations. So in these two type of bifurcations, the only stable state is the limit cycle. But here is what I just wanted you to remind you that you have a bistable state, but here you have also a monostable state, okay? So with this in mind, we can characterize these 4 bifurcations and say, well, how this works. For example, I want to see what, for example, this saddle node bifurcation gets me as a dynamical point of view. Is it bistable? Yes. So it's a bistable, this saddle node. Let me just go. Bistable because of what? This is the saddle node, because if you start here, fixed point, and if you start here, limit cycle. So this is what its bstability is. So it's bstable. Come on. Is bstable, and the question is, do these have a subthreshold oscillations? No. Okay, so before the bifurcation, if you are just, so you have oscillations in the limit cycle, but you don't have oscillations near here. So you have just a spike. So this is what we call a integrator, okay? And for example, and you can do that with all the bifurcations. So for example, the saddle node in the limit cycle, it's it's just monostable. Okay, it's not that depending on the initial conditions you can go oscillating or not. And why I'm just making these differences, because this will depend on what you want to model. So first you have to look at the data and see, well, what are my dynamicals, what are the dynamics of this data? And once you have it, then you want a model that represents the dynamics. And these bifurcations and these characterizations will help you to choose the model, okay? And again, so with this, you can have all, depending on if you want bistability or not, or if you want subthreshold oscillations or not, you can choose one of these. And say, well, I want, so my data is showing bstability and no subthreshold oscillations, well, I will just go ahead with the model with this, okay? And so on and so forth. So this is what I was telling you about. This will serve you when you are building models. But first of all, you need neural recordings. So if you are doing but you need recordings, you need data. And you can go from your own experiments, or you can get it from a collaborator, but you need data. So one approach is to, for example, if you want a model of a neuron, say, well, with this data, I know all the channels that it has and the kind of currents, and I fit the parameters and see what I can do, and I put that all in a model. But the problem with that is that you never know if you have measured all the variables, right? Because for measuring this, for knowing what kind of currents you have, well, you have to start, say, well, if I put a blocker of this channel with this change or not, but sometimes you don't get it right. So this can be a mess. And it can be another approach that determines what kind of bifurcation the neurons goes, and then use the chart that I was showing you before. So my advice, although these can be complementary approaches. So when you want to tackle a problem, you use all the tools you have, okay? But have in mind that this can be complementary. But knowing about the bifurcations can be very informative because it's a robust thing that does not depend on the details of the channels. So interdisciplinary work and respect the different ideologies. What I wanted to say with this is that if you are working with data, you probably are working with another guy with a different discipline. It can be a biologist, that I know. I've been interacting with biologists. I'm a pseudo-biologist, so it's a trick. But if you are using with weather, you are going to be using with meteorologists, or if you are doing whatever with word science or chemistries or engineers. And each discipline has its own ideology, its own way of approaching a problem. And it's not because, and the problem is not that, well, he doesn't know mathematics, he doesn't know dynamical systems as I do. That is not the problem. The problem is that the level of description is very different. And all these levels of descriptions inform to the problem. So you have to learn how to interact. And I will tell you more about it in the last talk. Okay, so before finishing this, I wanted to tell you a little about the Huxley model, just to give you a glimpse of how complex this could be. So an idea of, well, there are some of you that haven't seen this model. The ones that have seen it is a good moment to remember that. But just to tell you that this is very, very complex. And although there is still use, this kind of modeling is so complex that it's probably it's not the way to go. And it always depends on how you are focused, what are you going to extract from the data. If from the data you're just going to extract the spikes, then you don't need all the details of how this spike is generated or the specific shapes of the neuron. If you're just saying, well, I want to unveil the code, spikes or no spikes, then you don't need all this information. But if you're recording inside the neuron and you want to characterize the neuron, maybe this is the way to go. But I just wanted to show you different representations. Another thing that I want to highlight is that all of this started with great advantage in experimental techniques. So these guys this was after the war, so after the Second World War. Nobody wants to do anything related with weapons and all that. So they develop techniques to measure things that never had done before. So all of this started with experimental techniques. So this is why it's also very important to see how the advantages in the experiments can get you to a different science. Okay. Okay. So with their experiments, what they found is that they have like 3 major currents in this particular axon of the squid. Okay, so and they developed this dynamical system that what it says is, well, in the voltage you will have currents depending on the potassium, the sodium, and also a leak current, mostly from chloride ions. And we've seen this already. So the amazing thing of these guys is they not only provide the functional forms of this, but also the values. So these values were defined so that the equilibrium potentials, so that they redefine the values so that the equilibrium potential is at 0 and no one minus 70 as it generally is. But they can give you values of these equilibrium states, also at the maximum conductances, also at the membrane capacitance. So what these guys did was an amazing work of fitting these parameters. And this is something very difficult to do in general. So there was other times there were years, several years measuring, but I mean, we're still talking about these guys. So, and they could define, and one thing that it was important is that now we talk, let's see. Now we can think about this as ion channels and sodium channels potential. Back then, they didn't know there were channels, okay? The channels came like much further. They didn't know, but say, well, this is behaving like this. It has to be units, different units, so that this will fit my dynamical equation. So with the dynamical system, they can say, well, this has to be that n to the fourth, m to the third, and h. So they didn't know about channels, and they didn't know, but they say, well, this is behaving like this. So they could get the functional shapes, and finally, we can understand really how a spike is generated. So you have the stimulus, the applied current. So if you have a small applied current, you just have a small depolarization, and you have a repolarization, go back to the equilibrium. And in the gating, but sometimes you see a blip there, very small changes, but not so much. If you give a higher step in the applied current, so your value is 20-something microamps per centimeter square, then you have the action potentials. You have a large depolarization, and then the spike is like an exciting and repolarization, and then goes back in the refractory period where no spikes can be elicited here, and then go back slowly to the equilibrium. And you can see how the gating variables behave, and also the conductances. Okay, so here you have like all the details, what is happening with the spike. So this is a model, but this gives you predictions, and you can say, well, what happened if I just block one of these channels? If I just block one of these, for example, no conductance, what happened with the spike? You can play with that in the dynamical system, you can do experiment, and you can relate both of them, okay? Okay, so this is what we have, but again, to understand this, you have to understand the dynamics of all the system. That can be very complicated. So what we are going to see in the next class is a way of saying, well, if I am just only interested in the dynamics, maybe I don't need four equations, all this detail. If I just want a spike, maybe I can do it much more in a simpler way, understanding better the dynamics. And it always depends in this kind of things is what you want. What do you want from your models? And that is what will shape you what kind of model you want to build. Okay, so I will stop there, and we will continue tomorrow. Okay. If you have any questions, we don't have much time. But
perfect timing.
Great. You didn't speak so much as I wanted, but I think we were okay. But if you have any questions of anything, just is the time, or we can talk later, whatever you prefer.
No. Well, questions? No? Well, then I will start with a comment.
Okay.
Because actually, just for you to think about how difficult it is sometimes to decide how do you model something, because as Anna said, this is a beautiful model. The Huxley model took 10 years of development. They were lucky because they found that the squid has the biggest axon in nature. It's called the giant axon of the squid. It's not the squid that is giant, it's the axon that is giant. So, but the point is that this model is extremely complicated, and nowadays you can build a network, you can plug this model, but then you have noise, of course, and you have a complex network with different properties. So sometimes the emerging phenomena on a network with a noise environment, which is very natural, then you realize that things are that depend on so many things at the same time that all these the details about the model are totally irrelevant sometimes. Yeah? So you can simplify this a lot, and it still works perfectly to understand emerging phenomena in neural networks. Okay, so the point is that it's always nice to think about what you want to do first, at what level of scale, before going into the computer and doing something. Okay, yeah.
Yeah, yeah, and especially because nowadays, so this is just a squid there, dead or dying, and you just can play with that. But nowadays, you want to record the neuron activity while the animal is behaving. So inside, so you just measure some neurons, and then you want to know how all the network is behaving. So again, as Jordi is saying, that so it depends on what you want to, how you want to attack the problem is what you're going to do with your modeling. Yeah.
Hi.
Hi.
Going back to the chart you have with the 4 bifurcation types to choose the model you want.
So this one
Yeah,
or this one?
No, that one.
This
no, the other one.
Sorry. Yes.
Can you go back a bit more deeply on what do you mean by integrator and resonator?
What do you mean a resonator? So a resonator are the ones that have subthreshold oscillators. And what this means, so these are the Hoff guys. And so the resonators would be that the true limit cycle, if you want, is going to be this one. But the resonator, what happens is that before the bifurcation, you have like this behavior where you can still like kind of oscillate or even as this kind will be oscillating until it gets to the spiking limit cycle. So because of the dynamics, you will have these subthreshold oscillations. So you will still like be like going around until you get to the fixed point. Yeah, so
then the integrator, I'm not familiar with the terms.
So yeah, so the integrator will just go back to the equilibrium state. So that is the thing. So resonator, if it resonates, kind of oscillates. An integrator, it will just get your initial condition and they go back to the steady state.
Okay, thank you. So
yeah,
I understand the
it's
concept.
terminology,
yeah,
but
exactly.
yeah.
Okay, thank you.
Yeah. Okay, okay. So let's go to the next lecture. Yeah, I don't know how to ask the people in the Zoom if they. Do you have any question, guys? I hope not. I don't know how we are going to. Okay.